Hi, and welcome back for our last class of the semester. So today we're going to be talking about section 11.6, functions and graphs with polar coordinates. And when we talk about functions and graphs with polar coordinates meaning an ordered pair r comma theta, then when we talk about these functions and these graphs, typically what happens is that we want to write r equals some function of theta. In other words, you can write that as r equals f of theta. That is, the length of r depends upon the angle of theta. So we think of theta as our independent variable and r as the dependent variable. Now, this is a little bit different than, well, it's pretty similar, but there are some differences from our regular rectangular coordinates. So with our rectangular coordinates, you might think of an example like y equals x squared. And when we draw a picture of that, it looks like a parabola. And we think of y as a function of x, or y equals f of x. So in some sense, we have our independent variable, which is theta, and then we have our dependent variable, which is r. Now, one of the differences is that when we write an ordered pair from polar coordinates, we have r comma theta, and when we write an ordered pair for rectangular coordinates, we have xy. The difference is with the rectangular coordinates, the x is the input, which is the independent variable, and y is the dependent variable. Whereas when we're talking about polar coordinates, it's actually the opposite. That second variable, the theta, is the independent variable, and r, which is the first coordinate, is the dependent variable. Okay, so let's take a look at our first example of a function using polar coordinates. Alright, so our example is r equals 1 plus cosine of theta, and we are going to graph this function on the interval from 0 to 2 pi. Now, when you first started talking about graphing functions in college algebra, you might have started by plotting a bunch of points and then kind of connecting the dots. So we're going to try that here first. So what we'll do is we will create a table, and our input will be theta, and the output will be r, and our formula will be 1 plus cosine of theta. Now, when we graph this, we're going to be using our polar grid, and we're told to graph on the interval from 0 to 2 pi. So let's start with an angle of 0, and we'll plug 0 into our function, and we end up with r equals 1 plus cosine of 0, plugged in 0 for theta, and cosine of 0 is 1, so we have 1 plus 1 equals 2. So our r value is 2 and our theta value is 0. So when I go to plot that on my polar graph paper, I move my arm to an angle of 0 radians, and then I walk out a distance of 2, and so we have our point plotted 2, 0. Cool. Okay, so now let's pick another point to plot. So that means another angle that we're going to plug in. So kind of rotating around the circle, I'm going to pick another point, another angle. The one I'll choose is pi over 4. Okay. So we plug in pi over 4, and when I do that, I end up with r equals 1 plus cosine of pi over 4. And then I have to think about, all right, what is cosine of pi over 4? And I might have to do a little work, or I might have it memorized. And then I have 1 plus root 2 over 2. And if I type that into my calculator, that's approximately 1.7. Because we're plotting points, it's okay to make some rough estimates here. So our ordered pair is r is 1.7 and theta is pi over 4. So I find the angle of pi over 4 on my graph, and then I walk out a distance of 1.7 and I plot a point. Cool. So I can keep doing this. Maybe I'll choose maybe a couple of more points. I'll look at pi over 2, and you should check and convince yourself that when you plug in pi over 2, you get 1 plus cosine of pi over 2. Cosine of pi over 2 is 0, so 1 plus 0 is 1. And we plot the point 1 comma pi over 2. So I move to an angle of pi over 2, walk out a distance of 1, and plot that point. Okay. The last one that we're going to plot is, actually no, I have 2 more points to plot, is 3 pi over 4 and also an angle of pi. And so I would encourage you to pause this video and write down your R value for 3 pi over 4, plot that point, write down your R value for an angle of pi, and write down that point and plot it on the graph. So go ahead and pause the video and work those 2 points on your own. No, really, pause the video. Okay, well, hopefully you did pause the video, and once you turn it back on, you should check. These are the values that I got, that cosine of 3 pi over 4 is negative root 2 over 2. So we have 1 plus negative root 2 over 2, and we can plot that point. And our very last point is theta equals pi. And that point gives us an R value of 0 and an angle of pi. So I can swing my antenna around to an angle of pi, but I don't need to walk anywhere. Anytime your R value is 0, then your point is right at the origin. Okay, so we've plotted some points, but those points are kind of weird looking, and it's not really clear what this picture should look like. Okay, so what I might do is I might go to my graphing calculator and I might draw a picture using the polar graph capability of my calculator. Now for now, I want to just show you what this picture looks like. A little later in the video I'm going to give you some details on how to do this graphing on your own. But here's what this guy looks like. Alright, there it is. Now this shape, it has a special name. It's called a cardioid. And it turns out that this is kind of a cool shape, especially when it comes to microphones. If any of you do any sort of work in the music business or any sort of videography or anything where you need microphones, a cardioid microphone is a pretty well-known type of microphone. And these are called cardioid microphones because they pick up sound in this particular shape, this cardioid pattern shape. So I think that's kind of cool. But okay, so back to our picture. If we were to fill in the curve connecting those points, and we did a really good job of it, it would look like our graph from the graphing calculator. Okay, so I'm going to maybe draw one by hand here that looks like the graphing calculator gives us. So here's a hand-drawn picture of our cardioid on rectangular coordinates, or a rectangular grid anyway. And I can try and do a good job up on my polar graph as well. And if I didn't do any of the points along the bottom, but you hopefully you get the idea that if we had plotted points on that bottom half from pi to 2 pi, we would have gotten points that would lie along this cardioid. Okay, so I've left open a few questions. The first one is the question of, okay, how do we graph this thing on the graphing calculator so we know what the picture looks like? And number 2, is there an easier way to kind of think about what's happening on this picture and kind of visualize how to create some of these graphs? And we're going to address both of these as we continue. So we'd like to sort of understand where this cardioid comes from, and the way that we're going to think about it is we're going to think of that dashed black line as our antenna, and that is going to represent the angle, and that's going to sweep around this circle, and so from 0 to 2 pi, and we're actually going to see it go through twice. And so as this dashed line sweeps around the circle, you'll see that lime green line on there, my favorite color, with a red dot at the end. And for each angle along the way, what we'll see is that we have an R value, and that R value is the length of the green segment. Okay, so let's see what happens. Okay, so we see that dashed line swinging around, and that green segment is getting longer and shorter depending on what the R value is for that particular angle. So we sweep all the way around the circle, and along the way we get this cool cardioid shape. Able to graph functions in polar coordinates on our TI-84 graphing calculators. So the first thing that we want to do is make sure that we're in the right mode. So I'm going to click on the mode button, and there are a few things I need to double check. First of all, I want to make sure that my calculator is in radians and not in degrees. So we'll change that so we have radians. And then the more important part here, or the most important part, is the next line down has function, parametric, polar, and sequence. And we want to make sure that that mode is on polar. So here we are going over to polar. I hit enter, and now I can quit out of this part. All right, so now we are ready to graph. So I hit y equals, and the first thing that you'll notice is that our y equals is no longer there, and we have r equals instead, and that's because we're doing a polar function where r is a function of theta. Okay, so let's start with graphing the r equals 2 graph, which is kind of boring, but that's okay. We're going to type in r equals 2, and we'll start by doing a zoom standard. Okay, so we have our circle, and we expect to have a circle of radius 2, but the circle is kind of oval in shape. So ideally, when we're dealing with polar coordinates, we want to make sure that our axes are squared, meaning that the scale on the x-axis and the scale on the y-axis are the same. So what I might do here is I can go to zoom, and I can go down to zoom square and hit enter. And what that does is, whatever your axes were before, your calculator does its best job to make the scale on both axes the same. Okay, so if I now change this window, let's go into the window, I can see that our theta minimum is 0, and our theta maximum is 6.28, so that's roughly 2 pi. So this says that our calculator is graphing this function on the interval from 0 to 2 pi. Our x minimum and x maximum have been adjusted from -10 to +10. They've been adjusted to -16 to +16 to make sure that our scales are squared. The x-axis and the y-axis have the same length for 1 unit. Now, I may want to maybe zoom in on this picture, and it might make some more sense for me to maybe graph from -3 to +3. And then for the y values, I may also want to only look at y values from -3 to +3. And when I do that, and I hit graph, I've lost my zoom square. But that's okay. I can go back to zoom and scroll down to zoom square, hit enter, and now we've got ourselves a nice circle. Okay, cool. So that's our graph of r equals 2. Now, that's not really the most interesting graph for us. What we were wanting to graph here is our next example, which is r equals 1 plus cosine theta. So let's graph that one. We have 1 plus cosine, and then I'm going to use the variable button x, t, theta, n, and because we're in polar coordinates, instead of inputting an x, our calculator is going to input a theta. All right, so we've got 1 plus cosine of theta, and I hit graph and see what happens. And I get this pretty cool picture. Now, our calculator was already in zoom square, but in this picture, I can see that, I might want to adjust my window a little bit. I might want to get rid of some of these negative x values, and so maybe change my window to have an x minimum of -2 and maybe an x maximum of 4. And let's see what happens if we graph now. We still get this cardioid shape. And if I want to scale it so that a circle is a circle, I go down to zoom square and hit enter. Okay, so here is our picture of our cardioid. So what I'd like you to take away from today's class is the idea of what is a polar graph, a polar function, how do we graph these things. I don't expect you to become experts in graphing using polar coordinates and graphing functions like the cardioid, but what I would like you to do is to get a sense of sort of the nature of these functions. And so in order to do that, I think we should look at a few more examples. And again, I want you to kind of enjoy these pictures. They're pretty cool, in my opinion. And in your remote assignment today, you'll get a chance to draw some pretty cool functions as well. Okay, so our next example is r equals 1 plus 2 times the sine of theta. And we are going to graph this function on the interval from 0 to 2 pi, which is kind of the default unless somebody tells you otherwise. And the picture that we get is this cool looking, it almost looks like a cardioid, but with an extra little loop in there. And this shape, and shapes similar to this is called a limachin. And the word limachin is French for snail, so somebody decided that this particular shape somehow looked like a snail. So let's take a look at how this graph is created by looking at a similar movie involving swinging that antenna around the circle and seeing that length r and how it expands and contracts along the way. So we just saw the limachin being drawn, and I want you to rewatch this, and I want you to pay close attention to that little loop in the middle. And what you'll notice is that the green segment is actually going opposite of where the dashed line is. And the reason that that's happening is those are places where when we plug the theta value in, that the output, the r value, is a negative number. And you might remember from last class when we have a negative r value, that r value shoots in the opposite direction of the direction that the angle is pointing. Okay, so as we play this again, I want you to focus on the portion where we have the inner loop, which is places where the r value is negative. Our next example is r equals 3 times the cosine of 2 theta. And this graph looks like this pretty cool four-leaf clover here, and this is an example of a graph out of a family of curves known as rose curves. And the things that change on a rose curve are that you can change the number in front. So instead of 3, you can put whatever number you want there. And the other thing that can change is this 2 inside the parentheses. And I would encourage you, you'll see when we go on to the graphing calculator, you're going to see a few other examples of rose curves, but I would encourage you to change those values on your graphing calculator and see what the new pictures look like. Hey, so before we head over to the graphing calculator to check out some of the subtleties of graphing a rose curve, I want to look at this movie of the rose, and what I want you to focus on as you're watching this movie is I'd like you to focus on the portions of the graph, the angles, where the radius is negative, and those will be places where that dashed black line, which represents our angle, is opposite of the green line with the red dot at the end of it. So just like in our last example, when that green line is not lying directly on top of the black dashed angle, then what we have is we have a negative r value. Oh, so there is our negative r value. Okay, now we have a positive r value. And we go negative again. An example of a Rose curve of 3 times the cosine of 2 theta. And I want to talk about some of the subtleties of graphing some of these polar functions on the graphing calculator, that things that you might run into. So the first thing I'm going to do is type in 3 cosine of 2 theta. I already know my calculator is in radian mode, and under zoom I'm going to start with zoom standard. Okay, now I can see that I'm probably going to want to adjust the x values and the y values for this window. It looks like our Rose curve only extends as far as plus and minus 3 and plus or minus 3 in both the x and y directions. So maybe I will change, I'll go back to zoom, and, oh, nope, not zoom. I want to go to the window, and I'll go down to x minimum, which will be negative 3, and the x maximum will be 3, and the y minimum, negative 3, and the y maximum also of 3. So the x values and the y values just have to do with the viewing window. It doesn't have to do with what portion of the graph. It doesn't have anything to do with the theta values. Our theta values that we're plugging into the function are starting at a theta value of 0 and ending at a theta value of 2 pi. 6.28 is approximately 2 pi. Okay, so I hit graph, and yep, our picture is not looking, it's not looking that symmetric, so I'm going to go ahead and go to zoom and scroll down to zoom square. And now we have a nice picture where 1 unit on the x-axis is the same length as 1 unit on the y-axis. Okay, so this is a pretty cool picture of a Rose curve. It turns out that the Rose curve is a family of curves, and you can change things. For example, if you change the number in the front, that will change the length of the leaves. And if you change the number inside the parentheses, that value will change something different. So let's change this to, let's make this to a 6 and see what happens. Whoa, that was pretty cool. This is a pretty cool picture. Now, two things I want to say about this picture. The first one is that there's a lot more leaves, and those number of leaves have to do with the number that is inside the parentheses with the theta. So we went from a 2 inside the parentheses to a 6, and if you count carefully, you'll notice that there are 12 leaves there. Just an observation, not something that you need to worry about in terms of understanding for this course. The other observation is that these leaves on this rose, these petals, are rather pointy. And while that does look kind of cool, it kind of looks like a poinsettia almost, that is not actually accurate for the drawing. The reason that we're getting these jagged edges is because our calculator is not plotting enough points. So I want to go back to the window button and look down at the third line called theta step. And theta step says how many times the calculator is going to, how far the calculator is going to step before it plots another point and connects the dots. The larger this theta step number, the larger the step between dots that are being connected, and the less accurate your drawing will be. The smaller the number, the smaller the theta step, the more accurate your drawing will be, but the longer it will take to actually plot the function. So there's a trade-off. So right now we have a theta step of 0.13. Let's change the theta step to, let's try 0.1 and see what happens. Okay, it's a little bit better. You might even notice that the graph didn't quite connect at the end. That's because the last point that it plotted was here and it didn't know to go all the way back to the beginning. So let's make that theta step a little bit smaller. How about 0.01 and see what happens. Oh, nice. Now we get a nice pretty picture. I'm using my graphing emulator on the computer, and so this graphed pretty quickly. I bet for some of you, when you graph this on your graphing calculator, it's going to take a little bit longer to make that picture with the 12 petals. Okay, so the moral of the story is if your pictures look all jaggedy and pointy, there's a really good chance that's not how they're supposed to be. There's a much better chance that what you really need to do is make that theta step a smaller number so that your graph becomes smoother. Okay, so to wrap up our section on polar graphs, we're going to connect the polar graphs back to a technique that we used a few class periods ago. And so in this example, we're going to determine the theta values for which the graph of r equals 3 cosine of 2 theta intersects the origin. Okay, so this was our rose graph, and here it is again. And so we want to figure out what the angles are on this graph where the graph hits the origin. And so the thing that I want to think about is whenever I see the words intersects the origin is where the radius is going to be equal to 0. Okay, we don't have to extend that radius out at all. Alright, so looking at our function, we have r equals 3 cosine of 2 theta, and we're going to set r equal to 0, and we would like to solve the equation 0 equals 3 cosine of 2 theta. We want to solve that for theta. And our original graph only involved theta values between 0 and 2 pi, so that's what we're going to stick with. Okay, now to solve for theta, the first thing I want to do is divide by 3, so I really have 0 equals cosine of 2 theta. And you might remember back when we were talking about equations involving trig functions that if I have something fancy inside the parentheses, like 2 theta or b times theta, that number in front of the theta tells me how many times I need to search around the circle for angles to be equal to 2 theta. So we are going to search around the circle twice because we have a 2 in front of the theta. Alright, so when I think about the cosine function, cosine of an angle equals 0, that output of 0 is one of our, that tells me that the angle inside the parentheses is going to be a quadrantal angle. So my technique for figuring out what those angles are is to maybe look at the unit circle, and cosine is the x value on the unit circle. So the x value on the unit circle is equal to 0 at the top of the circle and the bottom of the circle. So traveling around this circle, so traveling first, I hit that first point at an angle of pi over 2, and then I continue swinging around the circle, and I hit that bottom point. That angle is 3 pi over 2, and you might think of this as blocks of pi over 2 all the way along, so 3 pi over 2, and then we go to 4 pi over 2 at the x-axis, and when we go back up again, we hit at 5 pi over 2. And then we continue around 6 pi over 2, and we hit that bottom line at 7 pi over 2. So that tells me, and I can keep going until I get back to the beginning, but those are my 4 points. And so that tells me that 2 theta is going to be equal to pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And to get theta by itself, I'll divide both sides by 2. And so dividing by 2 is the same thing as multiplying by a half. So my 4 final answers are going to be that theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And if I go back up to the drawing that we have up here, if I look at an angle of pi over 4, that's the 45-degree measure, here is an angle of pi over 4, and what I notice is that at that angle, the graph is right at the origin. Now, as I sort of swing along here, and I have these other maybe imaginary antennas, all of these antennas all the way along here, they all touch the graph where the graph is away from the origin until we get back to an angle of 3 pi over 4, and our radius there is 0. Nope, that's not a very good line. 5 pi over 4 and 7 pi over 4. Okay, so what we've just done is determine the theta values where our graph will cross or touch the origin. This particular question comes into play in Calculus 2 and in Calculus 3 when you start finding areas of different regions. So for example, with this rose, you might be finding the area of one of these leaves. So let's say that I wanted to find, or just wanted to draw, maybe this left-hand leaf over here. If I only wanted to draw just that portion of the leaf, then I could set my theta values. I could set my theta minimum to be the first part of that angle, so 3 pi over 4, and my theta maximum to be this angle of 5 pi over 4. And so if I did that on my graphing calculator, then that would just draw the one petal of this rose. All right. Well, we've now looked at some polar graphs. I hope you enjoy drawing some of the pictures on the remote assignment, and thanks for listening.